Right. So degrees of freedom means how many independent motions that a system can show, right? Now, as a simple example, if you take your arm, right, how many degrees of freedom are there? Can you count? How many degrees of freedom? Definitely our arm cannot show any translations because it is not going to move away from your body. It only shows rotations, right? You have so I was asking you how many degrees of freedom that you can have on your arm. One is at the shoulder, then one on the elbow, and then one other one rotation at your wrist. That is altogether 3. And each finger has how many independent motions? You can move finger in 3 different locations, right? So altogether 5 fingers will have 15 degrees of freedom, addition to the wrist, elbow, and the shoulder, right? So it is altogether 18 degrees of freedom, right? Because each part you can move independently. So that's how we calculate the degrees of freedom, and some systems do have infinite number of degrees of freedoms. That is also there, right? One example is the vibration of musical instruments. Let's say a string instrument like guitar or a violin. Right? Even though we think that hand is a very simple thing, it is not when it comes to the analysis of mechanics, right? It shows 18 degrees of freedom, and you know how much difficult it is with single degree of freedom, right? When it goes to 18 degrees of freedom, you'll see how difficult to control or to predict the exact motion of such a thing. Now, let's go with our most simplest system with 2 masses and 2 springs. Then we will try to derive the governing equation, and after that, let's try to solve this system, right? And I hope you can remember what we learned with the single degree of freedom systems. Now here what we're going to do is, since these two shows 2 different motions, we are going to write 2 equations, one for M1 and the other one for M2, and we are going to stick with the same notations. Velocity of M1 will be x dot 1, and this one x2 dot, and the acceleration is x double dot 1 and x double dot x2 double dot, right? Can you write the 2 equations for M1 and M2? Take few minutes try to write the equations for mass M1 and for mass M2. So if we write the equation for M1, so we have the spring force due to the expansion of K1, which will be exactly due to this X1 motion. So it will be minus K1 X1. This is the spring force, right? Then we are going to have another force due to this K2 spring. How much is that? K2, let's suppose it is in the positive direction. This can be changed, but that doesn't matter. It will be exactly X2 minus X1, right? The difference between these two motions. That's the amount the K2 spring is going to extend or shrink. And this will give rise to mx double dot 1 acceleration in the mass M1. So this is M1, right? In the same way, you can write for X2. In that case, what will happen? We have minus K2 X2 minus this K2 here, K right. Let's go for, since X1 is in the same direction, we'll take this also as minus value, which will make our life little bit easy. When you take it as minus, it will be X1 minus X2 and the other one is minus x2 minus x1 k1 should be equal to m2 x2 double dot, right? So this is the simplest system, but if we modify this even more little bit, there you have a system like this, which will be more practical. And another spring K3, and they are fixed. Now try to write the equation for this one. Can you do this one? You have were you able to write this one? So in this, what will happen? You have m1 x1 double dot, which is the inertia force, plus k1 spring into distance x1, plus the extension of k2 is x1 minus x2 equals 0, and then for the other mass m2 x2 double dot plus k2 x2 minus x1, which is the spring force from k2, and x2 into k3, right? There is addition term due to the last spring. Did you able to write this one? Now what we're going to do is we are going to arrange the terms little bit in simplified manner, so we can extend the same result for multi-degree of freedom systems, right? When you have 3, 4, 5, 6, 7, 8, whatever the number, up to infinite degrees of freedom. So what we're going to do is we are going to arrange them in using matrix, right? Okay, take few minutes and try to arrange these two equations in matrix form. Can you guys arrange it? Are there any questions? Are you following this? Anuga? Is it okay? You understand or any questions?
Yes, sir.
Were you able to arrange it in matrix form? It's not very difficult. What you need to do is, how many unknowns are here? You have x and you have the second derivative of x, which is the acceleration. So we need to have two vectors. One is the vector x double dot, which represent the acceleration vector. These are vectors, which is exactly this one, x2 double dot x. Right? So this is the acceleration vector. We call these vectors because, as you can see, there are only one column, right? So these are column matrices and they are typically unknowns. So those unknowns arranged in a column vector, so we call it as the vectors, and you have two different ones, one for acceleration and one for the displacement, right? Other than that, you have m1 and m2, which has to be multiplied only once with each term. So you get the spring inertia matrix M in this form. M1, right? M1 into x1, and the other one is 0, then 0, M2. This is not displayed at this one. And then the spring matrix, which will come in this way. K1 plus K2 minus K2 minus K2, and then K2 plus K3. So if I write the whole equation, it will look something like this. You need to arrange the terms a little bit to get this matrix. I think I tried to share the screen. This problem happens, right? So let's try to write the whole equation in matrix form, both equations together. First, we have the inertia matrix or the mass matrix M1, 0, 0, M2 into the acceleration x double dot, x2 double dot, right? Plus the spring matrix K1, K2 minus K2 minus K2, K2 plus K3 into the displacement x1, x2 should be equal to null vector 0, 0. Any questions up to this one? Now try to solve this one. It is same as what we did with the single degree of freedom system. Only thing is that you get, instead of one answer, there will be two answers for x1 and for x2, right? General form will be a1 sine omega t and a2 sine omega t. Right now, x1 and x2, these two are the forms. You can find x1 double dot and x2 double dot and put them in the governing equations. So we can write the two governing equations as minus M1 A1 omega squared sine omega t plus k1 plus k2 a1 sine omega t minus k2 a2 sine omega t equals 0. This is the first mass. And the next one,
Excuse me.
yes. What's the problem? Minus M2 A2 omega squared.
Excuse me.
Yes. Yes, you can ask.
Sir, we can't see the paper, sir.
Now is it okay?
We can't see the paper, sir.
Is it okay now? Because in my end, I am sharing the screen. Okay, let's try it again. Now is it okay?
Now it's okay, sir.
All right. I have some connection problems. It's not very good here. K2 plus K3 A2. You know how to get this one, right? Just put the values in your governing equations. Right? Now you can remove sine omega t because it is definitely not going to be 0. We will end up with these two simple equations. K1 plus K2 minus M1 omega squared into A1 minus K2 A2 equals 0, and from the next one minus K2 A2 plus K2 plus K3 minus M2 omega squared into A2. This should be A1, yes, equals 0. Right. Now let's see what are these A1 and A2. A1 and A2 are really the amplitudes of these two vibrations, or x1 and x2, because when you apply omega as 90 degrees, what will happen? X1 becomes A1. So they are the amplitudes, the maximum displacement that this each mass can show. So in this situation, to make things simple, what we do is, instead of going for the exact value of amplitude, right, we can always multiply it and find it. We are going to check what is the relative amplitude between first mass and the second mass. To make that, what we do is, we are going to divide the two equations with A1, or we can simply take A1 as 1. Right? This is, we are going to do, right? To simplify our work, we take A1 as 1. There's nothing wrong with this. Why? We are interested in the shape of the vibration, right? When you have the one actual value, you can just compute the exact value for the other one, right? When take A1 as 1, you get this one. Let me write it in one single paper. Right? We did this to make things simplified, right? Nothing else. We take A1 as 1, and relative to A1, we are going to compute A2. How much larger or how much smaller? So the target is to find this ratio between A1 and A2. Other things you can get from what you already know, right? So to do that, let's do a small example. Understand what's going to happen here. So this is the example. spring, the constant is K, first mass is M, displacement x1, another spring, again the value is K, and the next mass is 3 times M, displacement is x2. Now can you quickly write the governing equation for this system, M and Pm? So what would these two look like? You can write the matrix form directly, would be much easy. M, this one is 3M, 0, 0, this is symmetric. Or even you can take it as a diagonal matrix. X1 double dot, X2 double dot, plus. Here you should have the addition of the two springs, which will be 2K. And then use your matrix, which we derived earlier, to write this one directly. Minus K, this one is symmetric. And here you have K. X1, X2 equals 0. Vector. Right? From this, we can get this equation, but before that, we can simplify even that one and arrange it in a similar form. Then you will see that both of them are pretty much the same. Right? If I take this equation and this one, we can arrange omega squared term together. Omega squared minus sine. We have, just like here, M1 0 0 1 and 2. Right. Now for this one, Right? I wrote this equation for our equation 1 and 2 for the previous case, and we can use this system and apply it directly in our question now, right? This will make the long writings little bit shorter. So here we have minus omega squared related to this question. M1 is M0, 0, and M2 is 3M. And 1 and A2 plus any questions up to this one? Fine. Now, for this equation to have a solution, right? The determinant of the system should be 0, right? So we can take minus omega squared M plus 2k minus k minus k minus omega squared into 3m plus k, because we can add them. This is the same 1 A2.
So excuse me,
Yes.
we can't see the screen, sir.
Okay. I'll make it a little bit up. And I need to share the screen. Right, you can arrange it on your own. No need to look at the paper actually. Right? This equation we can format it to this type. Once you get this, one possible answer is this part becomes 0, which we don't need. But what we need is this one becomes 0. That means the determinant should be 0. So use that knowledge. Get a quadratic equation of omega, right? So to have solutions, the determinant should be 0. Omega squared m plus 2k minus k minus k omega squared 3m plus k. Determinant should be 0 to get non-trivial solutions. Have you studied this part in maths? Cramer's rule? Yes or no? Sometimes you may need a little bit of knowledge from your maths, especially determinants, then some useful theories in matrices, right? Especially if it is going to be higher degree systems, you will need those things. And who are doing mechatronics will definitely know these ones. Now simplify the determinant. So we have minus omega squared m plus 2k into minus omega squared 3m plus k minus k squared equals 0, right? And we can expand it and simplify. So you should get 3m squared Can you simplify it? So you should get how much? 3m squared omega 4 minus 3 7 mk into omega squared plus 2k and k is k squared, right? This is what you got? And then we are going to define two things. Phi, which will be equal to KOM, and lambda we define as omega squared. So divide the whole thing with m squared, 3 omega 4 is lambda squared minus 7 is there, m and m cancelled out, 7 pi lambda plus pi squared is 0, right? Now find lambda by solving this quadratic equation. Did you find lambda? Once you have lambda, you can find omega. It is the square root lambda. So apply the quadratic formula. Then you should get 7 pi plus or minus square root 7 pi squared minus 12 pi over 6. Which will give you lambda 1 as 7 minus square root 37 over 6 pi, and the other one 7 plus square root 37 over 6 pi. And you will see that both these are real positive values, right? Both of them. So related to this omega lambda 1 and lambda 2, we can got two omega values. Omega 1 will be the square root of this one. You can simplify and get the decimal values. Omega 2, we are only going to take the positive value here, because omegas are frequencies. So from here, point, check whether these are correct. This is what I got. And this one, 1.47 square root k over a. So now we have the natural frequencies, and you can see there are two natural frequencies, right? So unlike the single degree of freedom system, multi-degree or 2 degree of system freedom always have more than one natural frequency, right? The lowest one we typically call as the first natural frequency or the natural frequency, and the others we call them as harmonics, right? For 2 degree of freedom system, you will have one frequency and a right? So you will see that for 3 degree of freedom system, you will get 3 natural frequencies. Fundamental frequency, which is the lowest one, and 2 harmonics. If it is 10 degrees of freedom, you will get 1 fundamental frequency and 9 harmonics, right? Like that, it will go up. Now we can compute the relative amplitudes, and the relative amplitudes will give you the mode shape. What do you understand by mode shape is, it is simply how the system vibrates, right? X1 and X2, how it is going to move in this space. We call that as the mode shape. Now we have omega 1 and omega 2. So put these values in our equation that we got from the matrix here. This one. Use this line to find the value of A2. So you see that there are two A2 values relative to the two frequencies. So the first one will come from omega 1. So our equation is minus k equals to omega squared 3m plus k times A2. Right? I took it from this last line of this equation, right? So we can compute right. So you will get two values for this constant. So let's go for the proper naming of this one. This is typically noted as chi. So we get one value from one frequency, which will be 1.85. This is for omega 1, and the other one.
So we can see the screen, sir.
You can't see the screen. Okay. And the other one from omega 2, which will be, so check these values. I just do it in my own. Maybe they are wrong. The value from omega 2 is minus 0.181. Right? Now, how this is going to vibrate is as a combination of both these mode shapes and the frequencies. Remember, this is the general way of vibrating. So we have the mode shapes x1, which is related to frequency omega 1 as 1. Remember, we put 1 and 1.85. And the next mode shape x2 is 1 and minus 0.181. Check these values. Now to understand this better, let's draw the two mode shapes, right? We have two masses, M1 3M, now let's suppose this is the initial position. And this is 1, M1 will be here, then M2 should be at 1.85. And this is for omega 1, and for omega 2, what will happen? You have 1 at this point. This is 1, that's the motion of M1. And what happens to the other mass? It should go in the opposite direction, somewhere here, like this. So this is minus 0.181. So this is how the system now in omega 1 frequency. What is going to happen when M1 is moving at an amplitude of 1, M2 or the 3M mass is going to move at amplitude of 1.85, right? So that is what this shows. So M1 will move by 1 amplitude, then 3M is almost going to be double that amount. And in the second frequency, what happens? When M1 is moved at an amplitude of 1, 3M mass is going to move in the opposite direction. If this one, let's suppose, move to the right, then 3M mass is going to move to the left. In this situation, what will happen that in between the spring, in between M1 and M3, there will be a point which is not going to move due to this vibration. That point is going to be a fixed point. It is not going to show any motion. We call that kind of point as a node. So node does not vibrate. Right? So let's stop here. Do you have any questions? Go through this one again and also go through your notes and try to understand. We will do some more examples next week. Do you have any questions? So remember, 2 degrees of freedom, you will get 2 frequencies. Associated with those 2 frequencies, there will be 2 mode shapes or 2 different ways of vibration. And sometimes you can get stationary points even though the system is vibrating. We call those points as nodes. Any questions? Otherwise, we can wind up the session.
Sir,
Fine.
can you upload last week lectures?
The thing is that I can't do it from my home. I have to go to the university. These days, it is not very easy. Right? Once I go there, I'll upload everything.
Okay, sir.
Any more questions? So remember these things and also go through your notes. We will meet if possible next week. Right? Good night to all of you.
Okay, sir. Thank you, sir.
Good night, sir.
Good night, sir. Thank you, sir.
What's the question?
Sir, मैं lab group को हम ऐसे वें करगाना है?
Lab groups මම බලලා වෙන් කරලා දාන්නම්. හරි?
हरी sir.
මම
Thank
ඔක්කොම
you.
ඉන්නවා register එකේ මම list එක අරන් වෙන් කරලා දාන්නම්.
हाँ, okay sir.
සර් මාව මේ ලර්න් USL එකකට ඇඩ් වෙලා නැහැ සර්.
learn OSL එකේ. මම බලන්නම් මට පුළුවන්ද කියලා add කරන්න. හරි? නැත්නම් අපි IT
Thank
එකට
you, sir.
දාමුද?
Thank you, sir.
හරි. Okay then. I am going to end the session. No more questions, right?